Going to do these Atwood's machine problems from this Atwood's machine worksheet 1. In the notes I showed you there's really two ways to do these problems, and I'm going to try to do them both ways. The sort of shortcut way is just to look at, okay, the tension forces are going to cancel out and figure out like what's the actual forces in the line of motion that are causing the acceleration. So, and then there's the system of equations kind of thing. So I'll show you both, so you can do it whichever way you are more comfortable with. So we got a string attached to a cart on the top of the table like this. We're going to ignore friction. So that's good. For now, we'll be dealing with some friction soon. The mass of the cart is 1.8 kilograms, and its hanging mass is 0.20 kilograms. So let's draw the force diagrams. For the cart, of course, there's the force of gravity on the cart from the entire Earth, and that's going to be the mass of the cart times 10 every time. And then the support force, there's no motion in this direction, so that means the forces must be balanced on the cart from the, what is it, a table? From the table, track, whatever it is. And that must also be 18 newtons, because those are balanced. And then there's a tension force here on the cart from the string. And I don't know what that is. If there was friction, it would be this way, but there isn't. So that's it. The hanging mass here, I have the force of gravity on the hanging mass, which is its mass, 0.2 times 10. That's 2.0 newtons. And then the tension force. Now the tension force is the same as this. And before I draw it in here, I'm going to think for a minute about whether it would be bigger or smaller or equal to this. Okay? When we release this system, when we release this from rest, it's going to accelerate downward. Now that means that down must be the winning direction, which means gravity must be winning. So that tension force, I'm going to try real hard to make it look like it's smaller than that. So I can see that, or anybody else who wants to look at the diagrams can see that. It's a force of tension on the hanging mass from the string, and that is the same string as this. So those are equal to each other. Okay. If the cart and the hanging mass are released, what will be the motion of the cart? So we're looking for, is it constant velocity or constant acceleration? It's going to be constant acceleration. How do we know? Because the forces are not balanced. Forces are not balanced. That means you have acceleration. Are the forces acting? Are the forces balanced? No. Are the forces acting on the hanging mass? Are they balanced? No. Explain how you know. Because. Sorry, that's kind of like the same question. I'm just trying to really make that point because there is acceleration. And if there's acceleration, there's got to be unbalanced force. Determine the acceleration and show your work. So I think I might need a little bit more room. Oh, don't want to do it there on the other page. How about right here? Okay, so here's the, let's see, what should I do first, the long way or the short way? I think I'll do the shortcut way first, which is fine. You still have to show your work, but it's going to be a little bit less work. So the short way which is fine. You can do it the short way so long as you can manage the short way and get the right answer. If you're trying to do it the short way and you're not getting the right answers, then maybe you should try it the long way. So doing it the short way, what we're looking for is what is the unbalanced force. Sorry, I don't want to write that symbol. I'm not using that in this class. Total. What's the total unbalanced force, and what is the total mass times acceleration? So we just want to make sure that when we do the shortcut way, we're looking at the total unbalanced force on the system and the total mass of the system. So what's the total unbalanced force of the system? Well, the tension forces in all of these Atwood's problems, the tension forces are always going to cancel out, and they're not going to be part of the total here. So what's the total unbalanced force? Balanced, these cancel, so the total unbalanced force is just this. It's just the force of gravity on the hanging mass, right? Not to be confused with the cart. That's why I included this. And then what's the total mass? It's the mass of the cart plus the hanging mass times acceleration. So here, what's the force of gravity on that hanging mass? It's 2 newtons. And what's the total mass? 2 newtons. You know what 2 divided by 2 is? I bet you do. So there you go. That's what we get. Okay, so what does the longer way look like? The longer way, and you can see how it's going to turn into this after we get started. We're going to make 2 equations. Instead of doing this one equation with the totals, I'm going to do a Newton's law equation for the cart. So what's the unbalanced force for the cart, mass of cart times acceleration, and then for the hanging mass, what's the unbalanced force on that, right? So what's the unbalanced force on the cart? It's that force of tension. And I don't know what that is. I do know the mass of the cart. I don't know the acceleration. What's the unbalanced force on the hanging mass? Well, winner minus loser, so it's force of gravity minus tension. Force of gravity on the hanging mass minus the force of tension, and that's equal to the mass of the hanging mass. And now what's going to happen every time if you do it this long way is you are now going to add these 2 equations together, and notice that you will have a plus force of tension minus force of tension. That will always be true. Those will cancel out, and you get the force of gravity on the hanging mass, which is 2 newtons. Actually, let me just add the equations together before I plug numbers in. So I get force of gravity on hanging mass, tensions cancel out, and then 1.8a plus 0.2a, and it's going to be 2a, and you can see that it gets us the same answer. So the shortcut way, you could kind of describe the shortcut way as just knowing, you're like, well, look, I know the tension forces are going to cancel out, so I'm good there. I don't need to write out all that stuff. Here, we end up with the same thing here, right? It's just whether you set up these 2 equations or not. So it's up to you. I'm happy, whichever way you like to do it. You got to pick one. Try to get good at it. All right. So how about this kind of? This is like a full-on Atwood's machine. This is like the classic Atwood's machine here. Draw the force diagrams for masses m and m. So first of all, this one's heavier. So when we release this, this one is going to accelerate down, and this one is going to accelerate up. So that means that down is the winning direction here. Force of gravity on big M from the entire Earth is going to be its mass times 10. And it's accelerating down, which means down is the winning direction, which means that the force of tension on the big M from the string is equal to, I don't know what, sorry, didn't mean to write an equal sign there, but it's definitely smaller than this, because this is accelerating down. On the little mass M, up is the winning direction. So I'm going to do my force of gravity first. I like to do it that way. That's going to be 50 newtons, the mass times 10. And then I know that this one's accelerating up, so that means the tension force is winning. And there's only one string here. That's the same string, so that has to be equal to this. If you're looking at the picture and you're like, well, they don't look like they're equal, well, I never said I was going to draw these to scale. I'm not trying to do that. You could make an effort to draw them to scale, but I don't know. It doesn't seem like it's worth the trouble. If the masses are released, what will the motion of the masses be? It's going to be constant acceleration. Because forces are not balanced. Are the forces acting on m balanced? No. Sorry, it's the same thing. Are the forces acting on small m? No. Explain how you know. Because there's constant acceleration. Same answers as the last time. Just trying to make that point. And then determine the acceleration of the masses and show the work. So same deal. I'm going to do the short way and the long way. And I'll do it the same way. So this is sort of the shortcut, same way around. I'll do the short first. The shortcut way is maybe a little bit trickier here. So what's happening here with the unbalanced force total equals mass total times acceleration? The total unbalanced force, the internal to the system, just like in the last problem, the tensions are going to cancel out. So this is trying to make it happen, right? This is the direction of the acceleration. And this over here, this is like losing, right? But the more this mass, the heavier this is, the more gravity, and that's going to slow the whole thing down, right? So it's like this is winning and this is losing because of the overall, the shape of this, the redirect from the pulley, right? This one's going down, so that's the winning direction. This one's going up, so this is the losing direction. So at the end of it, what's happening here? The tension forces cancel out. This is winning, this is losing, right? Looking back at the diagram, this is winning, force of gravity on this. It's tugging on this, but it's losing to this larger mass. So the winners minus losers for the whole system is the force of gravity on the big M minus the force of gravity on the little m. And that's equal to the total mass times acceleration. And then I can plug stuff in. So I got 100 minus 50 is equal to 15 times a. So that acceleration is going to be 3.3, I believe. Right, 50 divided by, yeah, that should be right. Okay, what does it look like the long way? Well, we've got our two force diagrams here, so I can just do, this is the longer way. For big M and for little m, what's the unbalanced force equation? The unbalanced force acting on big M is winner minus loser, and the unbalanced force acting on little m is winner, tension's winning on that side, minus loser. Gravity's losing. And then not ready yet. So this is unbalanced forces mass times acceleration. This is the big M. And this is little m. And when I add them together, minus Ft plus Ft. Those are going to cancel every time. When I add ma and little ma, that gives me like the total. I'm going to get this exact same equation right here. Right? Get the tensions cancel out, and I get force of gravity on the big one, minus force of gravity on the little one, and then you know what the rest of the work looks like right there. So those are the two ways you can approach that. Whatever makes you happy. Well, maybe neither one of them makes you happy, but whichever one makes you less unhappy. How about that?